Can you see my screen? I was muted. Yeah, so I see one reaction. Okay. So I will talk about a parallel programming in general. Yes. And I will cover some general topics in parallel programming. So please let me know if the font size is okay, and yes, the speed I'm talking is slow or fast. So just let me know with some reactions. So we will talk about what is parallel programming, why do we need it, and where can we use it, and also a short introduction to parallel computing programming, and also the different or most common paradigms to write parallel code. So parallel computing is like an art, right, of writing code. And in this particular paradigm of programming, one writes the code so that different tasks can be executed on different computing units called cores, right? Simultaneously. So this is the essential feature, right? That everything that you are running, it's occurring simultaneously. So in the past, the computers were shipped with a single core, right? Pair central processing unit, CPU, right? And that's why in the past, if you talk about the CPUs, they were a synonym of cores, right? But currently, the architectures are more different than this. So when we talk about a serial program, right? So you will talk about hear about serial programs in several lectures. So it means that your program is using a single core, right? That's the meaning. And if your program can use different or several cores at the same time to perform some specific calculation, then we can say that your program is running in parallel. So the basic architecture that I mentioned before is now more complex. And the CPU, right, now contains more than one core, right? And for instance, there are machines that are now shipped with more than 128 cores, right? And we will take a look at how a machine Kebnekaise looks like. These are the common architectures that you can find in the different HPC centers. One is the so-called shared memory, right? Where we have several cores. In this case, I just depicted two for clarity reasons, but you can have, for instance, 128 on Dardel at PDC. And the main feature of this architecture is that all the cores share some memory space, right? So the second type of architecture is called a distributed memory. And in this case, we have different CPUs that are connected through some interconnect. So notice here that even though some cores here can share some memory, so in general, not all the cores share the same memory. Yeah. So how can one core on this CPU have information on the data that is available here, for example? So it can be done through some message exchange, right? But not just by sharing memory, as it's given here in the shared memory architecture. So the line dividing these two architectures is fine, right? It's not, sometimes it's not well defined, because as you can see here, we have some shared memory locally, yes, and also some distributed memory across all of these CPUs that are depicted here. So in the case of Kebnekaise, one of the standard nodes, we have the following architecture. And here you can see that there are 14 cores, right? And they are sharing some memory, yes, which is, in this case is 64 gigabytes, right? So they have access to this memory. And also in the same node, we can find another group of 14 cores. That's why we say that per node, we have 28 cores. So this is one of the standard nodes on Kebnekaise, and there are other nodes with also different number of cores, right? And the idea, or the basic idea, is similar. So the cores share some memory, and they are connected through some interconnect. So one particular feature when we are talking about the node level architecture, right, is that we have different types of memory, and the speed or the bandwidth of this different type of memory is quite different. So if you look at one specific core, for instance, the core with ID 0, you can see this type of memories called L1I, L1D, and so on. So the bandwidth, it's quite different, and there is a big gap between them. And for instance, if you are talking about the L1 cache, right? So the speed, or the bandwidth is in the order of the terabytes per second. Yeah. And if you are going further, right, to the global memory available for this course, so the bandwidth is around gigabytes per second. So that's why if you are writing a very efficient or fast code, in general, you are targeting these memory spaces. Note here that the storage, the size of the storage is relatively small, right? So you cannot put all the data you want, but only most relevant data here. And also, as you increase it, the size of the memory space is larger, right? Until you reach this whole global memory. So this is a trade-off, yes, between the bandwidth and also the storage size. So imagine now that you have this memory available, it's 20 gigabytes per second, but also you want to exchange messages around, yes, across the different CPUs. then the bandwidth is even lower, right? So that's why if you're writing some code that takes advantage of the shared memory architecture, in general, this should be a faster code than if you write it on the distributed architecture. So all these cores are arranged into the so-called non-uniform memory access architecture. And why is called like this? It is because there is a different bandwidth associated with the different memory spaces, as we have seen before. So this is the case of the CPUs, and we also have GPUs available. These are the graphic processing units, GPUs, and they are available at UPPMAX and also at HPC2N. And here you can see a big difference with respect to the CPU architecture that I mentioned before. Remember, in the CPU case, we had 28 cores for a standard node. But in the case of the GPUs, we have thousands of cores. Each of these little green square is a core, right? So you can see that in this type of architectures, you can have thousands of cores, right? So, but the main difference between each core in this GPU and one of these here in a standard node is that here the speed of each core is in the order of megahertz, right? And here it's in the order of gigahertz. So there's a big difference. And that's why here we can run many simple tasks, right? But that can be parallelized or run simultaneously easily. For instance, imagine that you want to compute the matrix vector product for a huge matrix, right? Then we can separate each element from the matrix, the row, and multiply it by the vector column and distribute it on each of these tiny cores, right? Also, the memory reserve for each of these cores is limited, and that's why we can only put little data on each core. It's not as in this case, right? That we have different levels of cache and also a very large global memory. So here, the calculation should be more specific, and also it should be highly parallelizable. And especially for linear algebra operations are suitable for this architecture. This is one GPU card, and on a single node, we can have several cards, right? And they are also connected, and they can share, for instance, the global memory in the node. So now let me talk about why the parallel programming is needed. So I wrote here, there is no free lunch when trying to use the features which include computing and memory resources in modern architectures. So imagine, for instance, that you wrote your Python code, and your code runs well, but because you didn't implement any parallel feature in your code, it will end up using a single core. Yes. Either it could be one of these in a standard node, or if you didn't write it well, maybe you will be using a single core of these GPUs, right? So your code needs to be aware of all the features that a single node or even the cluster is offering to you. So that's why you need to learn different techniques to make your code aware of all these features and leverage the power of the node and the HPC cluster. So you can write these features explicitly by coding them yourself, or implicitly by using some libraries. So some people are not aware that, for instance, most of the linear algebra libraries have already some parallelism, and this parallelism can be activated by external variables. So here is what happens in your local machine. So in your local machine, you may have some number of cores. For instance, in my laptop, I have 8 cores, right? And there is some memory that can be shared between all these cores, and they could be used by some parallel program. So, but of course, if you are working on a personal computer, so maybe you will need one core for running Word, another for running PowerPoint, Firefox, and so on. And then you cannot leverage the power of your laptop, your 8 cores, for instance, for your single application, because you also need to run your workflow, right? And here, this is the alternative of our cluster at HPC2N or UPPMAX, or even you can use some cloud service, right? Here is the organization. So I mentioned before that we have different type of nodes. I talk about one node, which is a standard one with 28 cores. And here is where you are sitting if you are logging into Kebnekaise or Rackham. So there are some login nodes. And here are the so-called computing nodes, where the production data is done, right? And they are accessed to the sbatch command. And you can see here that all these nodes have the structure that I mentioned before, the shared memory architecture, where we have several cores and they are sharing some memory. So as I mentioned before, if you have an application that runs only on a single core, then you will be underusing the resources, right? Although if your application is running well and you feel comfortable with that, then it is okay, right? So the situation, if you, for instance, on the other hand, allocate some resources, but you are not aware that you are only using one single core, then you will be wasting some energy and also consuming time from your project, right? So this is similar to allocating several washing machine and washing just a single cloth. So then you will be underusing it. So here there are some common parallel programming paradigms So first, let me review the threaded programming. So the threaded programming or shared memory programming takes advantage of the shared memory of the course that I showed before. And here threaded mechanisms can be used. So low-level programming languages such as Fortran, C, C++, use OpenMP as an standard API. Yes. And here all the threads have access to the same data, and then they can do the computation simultaneously. So in that way, you decrease the problem into N workers or N threads. So in the case of higher level languages, they could have some mechanisms to generate threads. And I wrote here that this can be confusing, especially if you use some linear algebra packages, for instance, LabPack Plus, because here these external libraries have their own threads, which in general is OpenMP threads, but the higher level languages could have their own threads as well, right? So as an example, in the case of Julia language, Julia has the so-called Julia threads, but if you are using some library like LabPack or BLAS in Julia, then these libraries can also have some threaded mechanism that you can activate. So don't get confused about this. The higher language level languages have their own threads and also the external libraries. So I wrote here that in the case of Python, there are the so-called Python threads, and in general, due to a lock mechanism, they are not efficient for computation. However, I found this a project which is called Mojo, right? Which is striving to leverage the power of Python in the thread mechanism, and also with other techniques that make the Python code really fast. Yes, but this is an experimental project. So in the case of the external libraries, one can activate the threaded mechanism by using environment variables such as this one for setting the number of threads, right? And just as a shortcoming from the shared memory programming, so we can have the data racing, right? Which happens when different threads can write on the same memory access. There is also the GPU programming, which shares several similarities with the shared memory mechanism. But here, one focus on the so-called kernels, which are highly optimized pieces of code, right? And also the APIs that are used in GPU programming are different. For instance, the NVIDIA and ROCm compilers. So besides this, we have the distributed memory programming that I mentioned before, where the different CPUs don't share the memory, but they can exchange data by using send and receive functions, for instance. And here, the message passing interface, API, is the standard for programming. So here I wanted to show you a simple code in Python, and this is a sleep function. I call it a sleep.py. And essentially here, what I'm doing is running a for loop, and then the code will sleep for 1 second. And because I have 6 iterations, then in total it will sleep 6 seconds. But here I parallelized the function, and notice here that the first thing that we need to think about when parallelizing code is that we need to do some code restructuring, right? As I did here. It's not like going from here and then getting some parallelization. One needs to refactor the code in some way that it's aware of the parallelism. So then this is the parallelization by using M processes, and this is the workload, and here is the beginning and the ending of the for loop for each thread. Here I am timing the code for in the serial case, and this the timing the code in the parallel case. And notice here that I am using the multiprocessing package in Python, that it's more on the side of the distributed computing, right? Because as I mentioned before, in Python, the threaded mechanism is not working well in the default version of Python. So how to run it? Just load these modules and type Python. And here you can copy the code with this button here. Copy and paste it in your script. So I have my script here. This is essentially this code, right? So I run it with Python sleep.py. Well, the modules are not loaded. I need to load it. And here you can see that the time in the serial mode was 6 seconds, and the time in parallel mode is just 1 second because I used for six workers. So the last thing that I will talk about is Dask, and Dask is a array model extension and task scheduler, and it allows you to distribute different tasks or different operations across multiple CPUs. It works well with NumPy, Pandas, and scikit-learn. And it divides the arrays into small pieces, and it offers some type of asynchronous computation, right? Where you launch different tasks, and then you don't wait for them to be executed, but they are just queued, right? So this is another workflow. Okay, that's it from my side. Is there any questions?
Yes, I can mention that we hope to include more about the task in the December course that we will have. The name on that course will be HPC Python.